Hello, everybody. Welcome to Pwning. Today, Nathan's gonna go through how to exploit compiled binaries. So, if you were here for my stuff 2 weeks ago when we were talking about reverse engineering, this is the evil side of that. So, I'll let him take it away. He's got the announcements, so I'm not gonna do them. So, go ahead.
Yeah, sweet. Just in terms of CTF team announcements for boilers, good work in Tokyo Westerns. I think we placed 6th in the US. That's right, Rowan. Yeah, I think it was 6th. Fun challenges though. Unfortunately, I couldn't play some of the pwns because I was too busy making these pwns for this demo. But next weekend, I think we're playing Dark CTF. Starts on 11 p.m. Thursday, so join us. And 2 weeks from now is our bootcamp CTF. So that's for everyone. Sign up for that if you haven't yet at play.ctf.boilers.net or .com. They'll both work. But binary exploitation. So assuming you're familiar with RE concepts here, if you're not, watch Rowan's day one presentation. That said, you'll still be able to get things out of it, but I'm going to be referencing back to a lot of things that Rowan talked about more in depth. And I'll be trying to watch chat. Rowan will be watching it as well, asking me any questions we have. And follow along with Docker. So this GitHub repo is where our demos are. You should be able to clone it, git clone, boilers/bootcamp pwn examples. Hopefully this downloads fine. But that's what you'll need to be set up for this. I'm mostly do pwns, but I'm the president of boilers, so do all sorts of stuff, help out here and there, make challenges. Yeah. So what is binary exploitation? This demo 0 isn't happening because we're basically going through a bunch of actual CTF challenges the whole time. So binary exploitation, often called pwn in a CTF, is what the category will be. Basically just making a compiled binary or program do something it wasn't intended to do. Usually this involves arbitrary code execution or memory corruption of some sort. Sometimes you just have to jump to a certain function that'll print a flag or something like that though. And also in the pwn category, you'll see stuff like Python sandboxes or bash tricks. But that's not what we're going to be talking about today. If you're interested in that, there's a bunch of great resources like Over the Wire Bandit for bash tricks or other tools, but not going to be what we're talking about today. We're going to be looking at compiled programs, and today it's just going to be C programs. So, common vulnerabilities. So I'm going to introduce you some of the vulnerabilities that we'll see today or in CTF challenges in general. So bash and shell tricks, as I mentioned a little bit earlier. So like setting the path to something, and if a program needs to access a program called cat, for example, but you set your path to have cat be pointing to something more vulnerable, then you can exploit that. Buffer overflows. This is writing out of bounds, overflowing variables, or further memory corruption. When you're spending a ton of time talking about buffer overflows. Off by one errors, you have a loop or something like that, that you have a greater than or equal to instead of a greater than or vice versa. And that might result in a buffer overflow or being able to break the program in a fun way. Function misuse, this is usually printf is where we see it most commonly, which we'll talk about probably tomorrow. Race conditions is stuff like accessing files out of order, or like you have one user opens a file and another user can modify the file after it's been opened, something like that. Or incorrect thread protections. And then input validation. So this is stuff like out of bounds array indexes where you just didn't check that they're writing a negative number. Common defenses that we're going to talk about: ASLR, PI, NX stack canaries. We'll have specific slides talking about this later on in this presentation. We'll be using techniques such as leaking stack addresses or leaking stack canaries, partial overwrites, stuff like that to bypass these. Tooling. So the main tools that we're going to be using is GDB with the Jeff plugin. PwnDebug is also good, but we're going to be using Jeff today. Python 3 with PwnTools, which is an awesome library for binary exploitation. Hopefully after this presentation you'll be somewhat familiar with it. And some general tools that have somewhat niche uses, but are all very useful. OneGadget, CheckSec, RopGadget. There's a couple others. CheckSec and RopGadget, I believe, are installed in the Docker, and we're not going to be using OneGadget today, but I will mention its usefulness. And then Ghidra and RE tools. Most of the time, a Pwn challenge will not provide source code, so you have to reverse engineer the binary, then find a bug in the assembly, and then figure out how to exploit that bug, and write a solve script to connect to a remote where the binary is running, and then get a flag. But in our case, I'm just going to be working from C so we can read the actual code. That'll make it easier to learn, and you can watch Rowan's presentation if you're interested in the reverse engineering side. So example number 1, getting familiar with PwnTools. So let's see, hopefully this cloned correctly. It didn't. Let's see. Do we have an IP? Git clone. Just gonna start the Docker again. Starting up. Oh, well, that. Docker PS. All right, what are we cloning? This guy. If you guys haven't cloned it yet, try to do that on the Docker. The using it on the Docker is important because offsets will be different. Okay, so this isn't working. So what is the Docker directory? This should -b. Okay. Um, Docker. Sorry about this, guys. It was working right when I started, and I wanted to just demonstrate cloning it, which apparently wasn't the move. But let's see, -v.
Yeah, so for everybody watching, this is what happens when you try and be fancy. Don't try and be fancy, just use the thing that works. Unless you're Nathan.
Can't have a relative path. What is path in Docker? Put it in the root directory. Okay. bootcamp pwn examples. All right, we have our examples. So we're going to be looking at example 1 right now. So you can look at the source code. It's a 53-line long program that apparently is some game, generates a number. We'll spend a little bit more time looking at this code later. I'm just going over a quick summary of it. It prints an item in a number list, which is defined up here in this game state struct. And then you're supposed to guess a secret number, which is loaded in right here. Supposedly impossible to guess. And then the score is calculated by whether or not you guess the secret number. If you guessed it correctly, your score is 1337. If you guessed it incorrectly, your score is 0. If you guessed it correctly, you get to enter your name. And then if your score is OX1337, which is a different number, because it's hex, then you win a secret prize. That's the quick summary of the score. And if you look at this makefile, this is how we're compiling it. GCC 0, so disabling optimization. And we're compiling it with debugging symbols, which is what this -g means. So if we run the make command, we should be able to have the binary, or it should also be provided when you cloned it. So it should be this example 1. We can run it. We can print number 1. There's some value that's random. We're going to guess the secret number. We're wrong, and our score is 0. So that's the general overview of program. One other thing I wanted to mention before we try to identify what exactly the vulnerabilities are here is this set vbuff at the beginning of a program. What set vbuff stands for set virtual buffer. You can set the line buffering to different modes. This 0 sets it to disabling line buffering. If you look at man set vbuff, you can read some more details. This will not work on your Docker, by the way, because man is not installed. But you can also just Google it, and you'll get a similar information. But what we do is we have a size of 0 and buffer of 0 and a mode of 2 in order to disable line buffering. So what this does is it just makes it, every time it outputs a character, it'll just print it immediately, and every time it inputs a character, it'll input it immediately. And this is just to make it easier to interact with the program via the command line and over the network. This is not in the Docker container, but you can clone that link and it will be. So right now I'm reading this file from inside the Docker container. Yeah. To connect to it, I used Docker run or Docker exec sudo docker exec -it and then the name of the or the ID of the Docker container and then the command to execute, so bash. That just means copy paste works because I'm in my own terminal. But yeah, that's what set vbuff does, and you'll see that at the top of pretty much all of our binary exploitation challenges that are written in C at least. So back to the slides. The first bug is in this area, this set of the code. Does anyone see what it is? So you can see up here, our struct is defined. If anyone knows what it is, drop it in the chat. But the struct is defined up here. So there's secret number, your number list, name, score. And then it prints out, it asks you which number to print after loading all of these things with random numbers. And it will scan integer choice. And then it will print the value of the number list at the choice. Does anyone see what the bug is? Anyone? Any guesses? Blindly reading input? So scanf %d reads an integer. So it will just read a number, and you can, overflow is a way of putting it. Usually it's just called an out of bounds array indices. You'll hear it often. Yeah, you can choose an invalid index. So if you look here at game state number list choice, if your choice is what value can you read secret number, assuming this is the order in memory. If we go to the code, sample one, actually I'm going to run this in GDB first. So GDB, let me get my notes up. Okay. So we can run, which number do you want to print? We're going to print, continue, 10. Okay. Print, let's see, do I have, oh, I'm inside read again. Pin. I should just be breaking it main. Break main, okay, run. So since debugging symbols are on, you can see the lines of code here. So if we run next, we can step to each line of code. It will initialize all of the numbers. Go through this however many times it takes. 16. Okay. It's going to print in which number do you want. Now it will scan our choice. But first, let's print number list. Not number list, it's game state. And then game state.number list is here. So you can see our secret number is been set to OX2B7. And then number list is this series of numbers. And since we mentioned that you can set an invalid index, I'm actually going to print game state in memory for you. So x slash, we'll print it as words. So 16xw game state, the address of game state. So we could see here 2b7, that corresponds to the secret number here. And then 18 is number list index 0. So if we were to give it an index of -1, 2b7, that should be printed, right? So -1. And if we look at, oops, I just ended the program, but Python 695 hex is 2b7. So using this approach, we should be able to just leak the secret number and bypass the first check. Which number do we want to print? -1. 513 is the secret number that we're going to guess. And we are right, and we have a score. And now they ask us to enter our name. And we do not get the Easter egg yet. So that's the next step. This is the bug that we're going to exploit to reach the Easter egg. Does anyone see where the bug is in this snippet of the code? If you look at the struct, you can see where the name is defined. And as people are starting to mention now that the time is syncing up, it is a buffer overflow right here with scanf. So scanf is with the %s argument, there is no length to the string. So you can do like %100s and it'll read a 100 length string. But this has no size. So it'll just read a name of however you want. And our goal is to overwrite score. So if we look at the code again, score is what is checked here. We need to set it to OX1337. And because of the way the memory is laid out, I'll show this in GDB. We can set the score to the value just by writing some more bytes at the end of our name. So let's demonstrate this in GDB right now. GDB 1, break main, run, and then we'll step through. Actually, I'll just break at line 27 so I can continue. And then we'll step. So we need to print our choice, which is -1, what was the value that we leaked? I'm just going to cheat and print games. Oh, we didn't even go through this line yet. It's up there somewhere. But I'm going to print game state and cheat. So 15E, 350. Next, 350. And since we are now the secret number, we set the score to 1337. We'll write, and we enter our name. So if we enter the name of 32 A's, 1, 2, 3, 4, 5, 6, 7, 8, 16, copy 32, and I'll just put a couple B's and C's here so that we could see where the end of our input was. And now we can print game state. We can see here that we had our 32 A's, and then score got set to OX424242, which this should not pass this check since we need to set it to 1337. But it shows us that we can control the score. So we just need to find the right values, set it to 1337. So we'll continue and program ends. But I'm going to show you how to use PwnTools to solve that. There's actually 2 more bugs in this code. I'm going to get back to that if you guys are curious and want to figure out what those bugs are. We're not going to bother exploiting them. But here we go. PwnTools is awesome. You can use Python to interact with it. Here are some just common patterns that we see in it. We can open a process. We can connect to a remote. This program is actually currently running on a remote, so it's running on my personal server. It's base 4001. I think it's 4001. Not sure which port I'm running on it. Oh wait, networking wasn't working. Yep. So I don't think I'll be able to demonstrate that, but I'll show you how to do it. It's pretty straightforward. You could see if you can make it work on your system. Netcat is a tool that we use a ton in CTFs to just connect to some service running on a remote. So it's probably installed by default on Ubuntu. If not, apt install netcat. I think you have to spell it out. I'm not 100% sure. You should just Google. And then PwnTools can write to processes. So stuff like p.send, send line will append a new line, and send line after, which is a concatenation of receive until and send line. Or you do send after. There's a couple variants. There's like receive until regex as well, or send line after regex. But it can read from process to p.receive, receive into the latest character. I think it has like a certain timeout as well. Receive line receives until you get a new line. Receive until, receive all will just continue receiving until you get an end of file. And then p.interactive for manual control. So I'm going to just start writing the solve script for you, and we can see where we end up. Solve.py from pwn import star. This is just common practice so that all of the PwnTools utilities are available. If you're doing Python software development, I'm going to advise against doing that. It's just not helpful for your IDE or code analysis tools and can result in bugs. But for us hackers, we only need our script to work once. So we're going to start by creating a process. Example, this is the name of the binary we want to use. And then we can do p.interactive. This will allow us to just interact with the process from our script. We can run it with Python 3. And you can see that it's just as if we're able to interact with it normally. So now we want to see if we can get past the first check. So print p.receive line. This will just print the first line we get. It's not really necessary here because we know that we need to send the first thing. We're going to send a line of -1 because that is how we leak our, actually I'm going to print, yeah, p.enter, all right. That is how we leak the secret number. So we should be able to send this and it advances. So we're going to actually use p.receive until now. A caret. And if we look over here, we can just put this up here, p.receive until, boop, and down here. And leak is, our leak's in there somewhere, the value that we have. Print leak, and then print. And we need to send our leak somehow. P.send line. We can use a regex here actually to extract the leak, or you can just use Python like split. So print leak.split. We'll do this for now. Solve.py. Our leak.split is here. So 1, 2, 3. So that'll be an index of 2. And so this is why Python's great, because you can use your Python's useful string manipulation. Strip or not split. Because a lot of times we're just parsing input in order to extract a leak or something like that. And so if we send our leak as a line, we should be able to make it past the next check. And now it's asking us to send our name to save the score. Wait. So now we want to, what was the next part? It was overflowing into our score. So we can, this goes after the leak. We can receive until a caret again. We can send a time. How many A's did we need? Example 1C, 32 A's and then the score. So A times 32, also why Python's great because of its string manipulation. And then plus P32 OX1337. So what is this P32 1337? Why do we have that? That is because the number is stored is Little Endian. And Rowan touched on this a little bit, but during the reverse engineering presentation, but didn't spend a ton of time on it. So let's see, Python 3. So the way a number is stored in memory is as bytes based on how it's based on the operating system and architecture. So if we print P32 OX1337, this is what it looks like on our system as bytes. So 7 is whatever. This is just the hex value of 7. So this is /x 371300. And if on a different system that is big endianness, so you can see that it's the other way around. So this is this is OX37, so it's OX37, OX13, OX00, OX00. In this case, OX00, OX00, OX13, OX37. So it's basically just backwards. But PwnTools can handle that for us, so we don't need to think about it. If we want to store a number in memory, we just write p32, the number. And integers are of size 32. On 64-bit, longs or pointers will be of size 64. So we'll be using p64 and p32 a lot. So we should be able to run this, and assuming it all works as expected, example 1, Python 3, solve. We should make it should work, but it doesn't work because it needs to be bytes. So p32 always returns a bytes object. In Python, you see this b in front of it, means it's a bytes object. So we need to make this a bytes object too. And with Python 3 PwnTools, it's just advised to make all of these bytes just to prevent issues like that. But it's not a big deal because it'll automatically convert it if it. So here we go. We found an Easter egg shell. So this gives us a terminal here, and we would be able to cat the flag if there was a flag. Let's see. Anything else I wanted to talk about here? Remote. So if we look at solve.py, to do this on a remote, oftentimes you'll want to make it working locally, and then PwnTools has awesome remote features, invade space 4001. And this will just work. A remote and a process have, for all intents and purposes, the exact same interface. So you can do remote.receive until remote.sendLine, Libc equals remote.receive until .split, and so forth. And this would work, assuming I had networking, which I don't. So that's that for example 1, unless anyone wants to see if you can identify these bugs here. I'm gonna just explain them fairly quickly. Don't have a ton of time, but srand will seed the random number generator, and time null is the current time in seconds. So this seeds a random number generator with a value that we can predict. So if we connect to the remote or run the binary at a certain time, we can just use that time, seed our own random number generator, and figure out what the secret number will be through that approach. The other vulnerability here is we take a modulo by 1,000. This is not impossible to guess. We could just run the program a ton of times to brute force the number, which is, we sometimes see that in CTFs. Either a trying to like guess a number type thing, or just brute forcing an address, for example. All right, the next example, we're going to be looking at a stack buffer overflow. Let me pull up my notes for this guy. Example 2. All right. See, so if you look at the code here, it's actually the same as on the slide, so I'll use the slide. Can we see what the bug is here? It's in this line right here, because all the other lines don't do anything except for initialize. This uses the function get, which is just about the worst function known to. So man3 get. This gives us the documentation on gets. Git says never use this function. So I advise against using git. It's impossible to tell how many characters it'll read, so it will overflow, which is essentially the exact same thing as %s in scanf. But now we need to figure out a way to exploit this program in order to reach an address of a different function. So we need to hijack control flow this time rather than just overwriting a variable. So I'm going to remind you of what stack frames are and what they look like. Rowan talked about this in his reverse engineering slides somewhat extensively. I actually hijacked the slide directly from him. So every time function's called, stack frame is created. It looks like your return pointer is on the stack, then base pointer, and then stack space. So stack space is like these variables such as buffer. So your buffer will write, and after your buffer comes RBP and RIP. So this is the reason it's oriented like this, because of the direction that stack grows in memory. But when you read into a buffer here, it'll read in this direction. And then when you return, it will pop the saved RIP, and that's the address you're going to, and it'll pop RBP into the former base pointer, or the now current base pointer. So we can look at that in this example. So libc start main is the function that calls main. So we can actually see this real quick in GDB. Break main, run, backtrace. Nope, info frame. So you can see that the saved RIP is this address. Info frame's actually quite useful when dealing with binary exploitation and overwriting the return pointer, so you can see whether or not you successfully overwrote it. 10i. So you can see that this is in libc start main, the address that we're returning to. So that did end up calling it, and it'll return to this, and then it'll just call exit with the return value of main, which is returned in EAX. If you remember the system V calling convention that Rowan talked about. So here's our buffer. We write into it. We can overflow saved RBP. We can overflow saved RBP, and we can overflow variables of main and so forth, and essentially hijack the stack. So I'm going to demo this with PwnTools and just writing a solve script. But first, we're just going to show it in GB. So 1, 2, 3, 4, 8. 1, 2, 3, 4, 5, 6, 7, 8. If you remember, our size was 16 bytes. And then it's saved to RBP, so this should be 1, 2, 3, 4, 5, 6, 7, 8. It's 8 bytes because that is the size of pointer on 64-bit Linux. And then our IP, it will be the next 8 bytes. 3, 4, 6, 7, 8. And we see we segfault. A segfault occurs when we try to access memory that we can't access. Say, for example, attempting to return to OXCCC, or that value. You can see the RBP was popped as Bs. This happened in leave, and it did not crash the program there because it just sets a register that doesn't try to access memory. Whereas this does crash because it tries to access memory at these Cs, which is impossible because it can't execute anything that doesn't exist. So how will we exploit this to get a shell or get to win the CTF challenge somehow? If we look at the code itself again, we can see that there's this win1 function and this win2 function. So if we look at this win1 function, we want to so it has an address, and we can change the return address with this get to the address of win1. So if we look at, let's use a short solve script to do this. From pwn port star process example 2. The common practice is to set a payload. So payload equals bytes payload. This just allows us to, when it gets more complicated, we might have a really long payload. So we can just slowly build it up. So bytes A times 16, or was it 32? 16? 16. So this is buffer. And then we can do P64, remember, because we're on 64-bit and we need an address or the register size for RBP. Where did my slides go? Here we are. So this will be the address of RBP, which doesn't matter because it's the saved base pointer that will be restored for this new function. But if it's at the top of a function, it's going to act as if it's calling a new function. So it's just going to save the base pointer again, if that makes sense. I can actually go back here. So this is the top of a function. It pushes RBP, and then it sets it to RSP. So when we're jumping to the top of a function, this doesn't matter. And if we're jumping to something that doesn't use stack space, this doesn't matter. If we're jumping to something in the middle of a function or that does use stack space, we will need to pay attention to what RBP is set to. And then we want the address of win. So we can get the address of win with GDB, print break, or print win. We actually have to start the program, then we can print win. Win one. There we go. So this is the address of win. And because I'm able to copy paste, we can just put it right here. This is the new return point. Send line payload. And then we could do p.interactive, which will automatically receive all the input and allow us to interact with it if appropriate. We can run the solve script. Got an end of file, and it's segfaulted. So apparently we did something slightly wrong. But since I don't remember what it is, I'm going to show you how to debug with PwnTools, which I meant to do on the first one, but we can do it here too. Process.gdb.attach. Process is a awesome PwnTools feature. GDB comes from PwnTools in this case, it's imported. And we can also give it some commands to execute, but we don't need any right now, right when it attaches, because it'll automatically break for us. And sometimes we also need to set our context.terminal. This is the command that is executed to create a new terminal. If you're in just a regular terminal, I think it should just work. If you're not like SSH like I am, but it really depends on your machine. So I'm going to use tmux split window horizontal. And this can be configured however you prefer. If you're inside tmux, which I'm not yet, but tmux is a terminal multiplexer, which is quite useful for just like you can split terminals and just have multiple things going on. But a side note, self-pi. Okay. So you can see here, it'll just split automatically and continue running. So we can type the fin command to, right now it's in the middle of gets. So we can type fin until we get back to main. We can go step instruction. So we see it leaves, and then it goes to this function. And we see that this is our address that we wanted to jump to. And it is the address of win. And so if we continue, it should print something, but it doesn't because I had a weird bug when creating this challenge. So what's actually happening here, if you're curious, is XMM0 is very large, so it needs to be aligned by like 16 bytes instead of 8 bytes or something wacky like that. I'm not 100% sure what the issue is, but because we're jumping to printf at this at this time in the program, it doesn't work. But we can actually, I'm actually going to start by introducing what ROP is, and then I'll go back to this one and show us how we can fix this issue. But Next up, so that time, like, you could see that it worked. So we did jump to win. But calling win2 is slightly different because if we look at the code, example2.c, win2 asks for an argument, and it calls system with that argument. And system is, if you're not familiar, man3 system. We do 3 because 3 specifies which like set of man pages, so it'll give you like the C library calls, library functions, and how they work if you do man3. Otherwise, it might give you something else. But it turns out 3 is the first one. System's the first one that shows up anyway on page 3. So it uses fork and creates a child process that executes the shell command. So we can run binsh, for example, and we would get a shell and be able to access files on the system. So we need to first remember the calling convention. Can this exploit in particular, without anything special going on, it wouldn't really work with stack protectors on. So a stack cookie would be able to prevent you from overwriting it directly. In some like cases, you can leak the stack cookie or brute force it. On 32-bit, for example, if you have the patience, it's not too hard, or it's feasible to brute force a stack cookie. But yeah, hopefully that answers your question. So the system v calling convention is, Rowan talked about this a bit as well. So arguments are passed in registers first, RDI, RSI, RDX, RCX, R8, R9, in that order. And then everything else is passed on the stack. Then return values and functions must preserve values. It's not important in our case because we just want to call a function. So what we need to do, set RDI to binsh if we want to execute program binsh, which is convenient because that's just a short way to get a shell. So how do we set RDI to that value? It's the first argument. We use a technique called return-oriented programming. So what this means essentially is you can throw a return in here, and if this like stack isn't touched, the stack pointer just moves down once you like pop RIP with a ret instruction, and it will just, if there's another return, it'll just try to return to whatever's next. Here we are. So we use what are called gadgets. They're short but useful instructions, usually followed by a return. Stuff like pop RDI ret, increment RX return, syscall. There's some other like jump to an address call function that you don't need a return after, as they do something very specific like that isn't expected to return. Or a function call will actually just be able to call the function because it pushes new stack information. It'll still return to whatever your ret's pointing to next. Tools like ROP-Gadget are great for finding these gadgets. I'll actually demonstrate right now. ROP-Gadget should be installed, yes it is, on the Docker. So ROP-Gadget example 2, ROP-Gadget -binary, example 2. And we get a boatload of gadgets. You can see like what these gadgets are like. So pop RBP, there's pop a series of registers, push some value and jump to an address. Some of these are quite useless. Like unless whatever's at this address is important, we'll never use this gadget ever. But we can look at what this actually ends up looking like in memory right here. So here's our buffer. We overwrite the saved RBP. And then we put the address to this gadget. So pop RDI ret. We can actually, if we can find a pop RDI gadget. Wrap gadget. Wrap gadget has tools to search for gadgets, but I just like grabbing the output when the binary is not massive. We only have 92 gadgets here because the binary is somewhat short. But we do have a pop RDI gadget at this address. So we take this address and we'll put it at the end of our perm. So if we can do this right now. Yeah, we can do that right when I get back to that. That'll be awesome. So we can see here this will pop RDI. And we now want some value. Oops, I'll just, okay. And then this is whatever value we're putting into RDI. This is like C's or D's or something. So we can run this. Hold up. We're attaching GDB. Okay. So we're going to get up to our return in main. And we can see that we overwrote this value to our pop RDI. So we step here and we actually jump to this address, pop RDI. And it grabs the next value on the stack and puts that into RDI. You look up here, our register RDI is set to a bunch of Ds. And then we can return and we should just, it's gonna segfault because we didn't put anything after that. But we see that it did try to return to the address after that, which is what happens here. So in order to get a shell or call win2 correctly, we'd want to set a pointer to binsh there into RDI. And then we would call win2 with that argument. So in order to find the address of win2, we can, if we actually look at the source, example 2.c, we see that our binsh string actually exists in memory. This is kind of sneaky because it's just at the end of some string. But if we give it this pointer right here to the middle of the, to the beginning of /bin/sh, it ends with the null byte and we're all good. So we can actually find that address in GDB fairly easily. Break main, then just grep. This is a tool in GEF, not built into GDB. This will just scan the memory for a certain string. Run. Okay. And so you can see I found a couple references to a string. So there's one at this address, one at this address, and one at this address. We're going to just grab this one up here. This is actually in Libc, you can see here. So this will be loaded because of ASLR, which we'll talk about shortly, into different locations each time. But these two, I believe, will both be in the binary. It's actually, binary just looks like it's loaded in two different places, because it's, you see it ends with 79C both. But you can grab that. Solve.py. Put that in there. Setting this to be a pointer to binsh. And then we want the address of win2. We can also do this with GDB. Win2, same idea as with win1. GDB, run, oh, I just need to run the solve.py. And assuming all goes according to plan, it works. but it doesn't work because of the same issue as before. I don't know exactly what's going on, but you can explain that, Rowan, while I show how to make the last one work, or the first one
Yeah.
work.
So DM from our team popped into my Discord DMs, haha, and explained exactly what's happening. So basically, the move APS instruction will, the instruction itself will cause a segmentation fault if the memory is not 16 byte aligned. So it's actually a pretty common problem when jumping into printf, because if we have a move APS that expects it to be 16 byte aligned, we're not 16 byte aligned. If you've wrapped into printf, then that's going to cause an issue. So that is why that's happening, and it can be solved with exactly what Nathan's doing now, which is a wrap to single ret and then right to where we are trying to hijack to, which in this case is the win function.
Yes. So you can see here, we just throw in a ret, which just does absolutely nothing except advance the stack one instruction, which is all we need to get this aligned correctly. We should be able to run solve.py. I commented out all the other lines about other functions. So you see here, or the other ROP other than just win1. So here, you win. Now try to use this program to call binsh. And now we're going to fix our offset in this as well by just, we're going to do the exact same thing, except with the extra ret in the beginning. And if this all goes according to plan, it works. And it does work. So you see here, the program is still running, and we have a shell. So cat flag. We don't have a flag, unfortunately, but that's how it would work. And I'm also going to show how PwnTools can make this even easier for us. So I'll show with the first example first. So we have our ret. I'll just keep that here. Lazy. And you know how we looked up all these addresses? It's a lot of hard work. PwnTools can do this for us. So binary equals elf example 02. And then we can just do binary dot symbols win1. So PwnTools will just open up the binary and dump whatever information or gather whatever information it can, which includes the addresses of symbols. And Python example. You can see that it just has whatever the addresses of all the symbols are. And win will be in here, printf, whatever symbols are in the program, win2, you see hex. This is the address of win2 that we had got earlier. So this makes life much easier. You'd see that this should still work. Python 3. Py. And you see we were able to get win1 to print this string. And did I want to mention PwnTools also has a ROP utility. So ROP equals ROP. So we can just do, we'll throw this right here. PwnTools can search for this with, I think it's ROP.search or something like that. You can like search for a specific gadget. Or you can just use PwnTools to payload ROP. Yeah. ROP.call win2 is the function we want to call. And the argument we want to call is, we're going to search this binary. So this is what we loaded with the elf. So we can search it for a certain string. Which we're searching for binsh followed it by a null byte. which grabs its this address for us. And it wants a list of arguments. This returns an iterator binary.search, so we need next to just grab the first item in it, which is just a Python thing. And then we can, that's the ROP, and then we need to print, we can just print it, ROP.dump, it'll like pretty print it for us. And then we can payload ROP.chain, which will convert it to bytes for us. And that should also work. I'm going to comment out this GDB line so we don't have to continue each. I missed a closing something. Binary.search, next. There we go. That's good. I did mess something up. But you can see here it's win2. And oh, I know what the problem is. We also need to set, when it's generating a ROP chain, it thinks it's in 32-bit by default. So we're going to tell it it's not with AMD 64, which is the architecture that we are on. You'll need to pay attention to this a bunch when using built-in like PwnTools stuff. So it's some automated format string stuff, automated ROP, a bunch of useful tools like that. Make sure you set context.arch. Context.arch. And you can see we have a shell here. And this is the ROP chain that was built, which is the exact same as ours. It found the pop RDI instruction itself. So it was able to just search the binary for that. And then it set RDI, and then it called win2. So that is the example 2. I'm gonna have a little bit of time for just a quick break right now so I can grab some water, and because it has been a bit of time and we've got another 2 examples to go through hopefully. So Rowan, you wanna throw up a quick break screen if possible?
Muted. Yeah, I can throw up a break screen, or I can just go ahead and do a demo if you'd rather.
Sure, you wanna go ahead and do a demo? I'll be back in
Oh,
like 5 or 6
maybe
minutes.
I can't. I'm on Windows. Just kidding.
You can read some random write-up on the internet if you want.
I'll just read my own write-up.
Sweet.
If anybody has any questions while I'm pulling this up, go ahead and just drop them in chat, and I will give you the best answer I can. Anything Nathan's talked about so far, or anything that he has not. Nothing? All right, well, we're almost there on getting this example up. Oh, all right. Alright, well, I am getting merge conflicts currently, so.
That's fine. I'm just getting back from getting my water, so I'm gonna
Alright,
pull
well,
up
I
stuff.
didn't I didn't
You can
demo
tell a quick
anything because I
story.
wasn't ready. Uh, hmm, quick pwn story. Let's see. Well, so here's a good one. So our teaching assistant, Nathan and I's teaching assistant for CS 527 had some really excellent challenges. CS 527s are graduate security offensive pwning class essentially at Purdue. Had some really excellent challenges, but they were also really hard. Um, and there was one challenge that I worked on for I think it was like 3 or 4 straight days. Um, so yeah, there's the first lesson. Don't be afraid to work on something until you just until you get it. Um, second thing, um, pay attention to what you're looking at because the first thought I had was, oh, I can I can do this thing called stack pivoting, which I think Nathan is probably going to talk about on Friday, or not at all. But essentially, what stack pivoting is setting up um, your fake stack in some region of memory and then adjusting RSP and RBP to point to your created stack frame instead of the actual stack frames that the program has created thus far. Um, and you can do that by a lot of different methods. But the most fun that I had with it was waiting 4 days until I realized that the instruction ret number will actually return a relative address on the stack. And so you don't actually need to leak the stack if you know how many bytes away from your ROP you need to go. So that's fun. Anyway, back to
Stories.
Nathan.
Back to Nathan. Nathan's gonna talk about shellcoding, ASLR, and NX. There should be a comma here. It's whatever the like inverse of the anti-Oxford comma is, not having a comma at the beginning. But I skipped over all of the exploits that use an executable stack, just because we don't see them a lot now, but they definitely had their place in history. So before ASLR and NX, address space layout randomization, and non-executable stack, it was the easy technique to use. So what you could do is you could overflow a buffer, put your shellcode in the top of the buffer, then overwrite the return pointer at the end of the buffer, as we did here, overwrite this return pointer, and the address you would set it to would be this address, the address of your buffer. But it doesn't work now for two reasons. ASLR, which means the address of buffer is unknown, and NX, which means you can't execute any code at buffer because it is on the stack and the stack is not marked as executable. I'm going to talk about that in a little more detail. This is what ASLR does. So if we look at process maps of a program, this is an example of a program with ASLR enabled. So you can see that the address of the binary itself is at OX 400,000, which actually will be the same every time. But you can see that the address of Libc and LD, 7F267, this is a random address. These bytes are all random. Not the 7F at the beginning, and not the 3 zeros at the end. So this is based on the page size, and this is just standard because it needs to be at the near the top of the memory space. So you can also see that Libc and LD are close together in memory. So this means this actually depends on your operating system. I was just looking at the other day. But in this case, if you have like the address of something in Libc, you can calculate the address of something in LD or other libraries. And then you can see the address of stack here, which would be where buffer 16 is. This is random, and you can see that it's very far away, many bytes away from the library addresses. And see the heap is not here, but if the heap is used, it would also be at a totally different randomized address. And vsyscall, it's worth noting, just because sometimes you run into it, it's fairly rare, but it's always at the same address, whether or not ASLR is enabled. There's not a ton of great gadgets there, and it is very short, but it is executable. What this means is basically just redshift, which means only a return, which is exactly what we had to do to get an address over, but this basically allows you to reach something lower on your stack as a more complex technique that I won't be getting into any further than that, side note. And pi is position independent execution, another protection, a lot like ASLR, but what it does is randomize the address that the binary is loaded. So you see this is example 3. This would be example 1. This one has ASLR enabled because that's a system-wide thing. But this is how your binary is compiled with or without pi. So this one's without. You can see OX4000. This one, random address. Each time you run it, it'll be different. These last 3, not bytes, but half bytes will be the same. Last 12 bits will be the same throughout the entire program though, but the rest randomized. And you see ASLR is also enabled here. See that the addresses are different, the previous one. And so I'm going to talk about example 3 now, which is how we get past ASLR and pi. The technique that we're going to be using, let's see, do I show the code? We're going to be using partial overwrite. I'll look at the code real quick. It just calls go, and go calls read input, and read input reads your input. And this is also vulnerable to a buffer overflow. The stack protector is disabled, as someone mentioned earlier. And this allows us to overflow to try to call some function. But we don't know the address of that function. So if we gdb print break main run, see the address of main here? Something wacky, because it is randomized. GDB actually sometimes will load it into the same place each time, depending on like whether you're using GEF or not. So you can run set table off, and that will ensure that when you run it, it'll be at a different address each time. So see, I'm starting a new program each time I'm running run, and it's loading in a different address. So we want to jump to win, but how can we do that if we don't know its address? Run, and then we can print win, run, print win. See, it's a different address each time, but as we mentioned, the last 12 bits are the same. So what this sometimes means is we'll actually go to we'll continue execution till go, step inside go, and then we'll step inside read input. Okay, so this is where the buffer overflow is occurring. So we can info frame. We can see the saved return pointer, which is what we will be overflowing. And we can print the address of win again. Can see, compare these addresses. Because the offsets are the same and they're in the same binary, we actually can see that this is all the same. We can actually use subtraction to prove it. They're only different by, like, not a lot. The return address and the start of win. If you also look at the code, you see that win and go are right next to each other in memory, which makes sense. So if we have the ability to overwrite just this byte, and because of little Indianness and the way it's stored in memory, we can. So if we actually, this is the stack right here. Slash 64xb bytes. We can see here that we'll overflow into the one that ends with A7. It's actually right here, it seems like. But when we overflow into it, we can set, this is the byte that will be set first. And if not a null byte is not appended, then we can change this to just 2A's, and we should be able to jump to win. So here's that explained in a slide. So because the less significant bits do not change, the 3 least significant half bytes or last 12 bits, they're from the elf itself. So we can actually use PwnTools or GDB before running it. We can print when you can see that this is what is actually saved in the elf, and the other information isn't stored anywhere. And it's because the way pages are aligned in virtual memory, which I won't get into too much detail about. So if we overwrite that least significant byte, if we were to try to overwrite 2 bytes, we could do it, but because this is randomized, this 6 right here, if we wanted to call something more complicated, we would need to brute force. But since these are so very close together, we only need to overwrite this byte. So you can only write 1 byte at a time. So up to 3 total bytes can easily be brute forced. You'll see 12-bit brute forces in like heap exploitation or a bunch of other places, which is a similar idea because the addresses are randomized. And if you run a VPS in the same EC2 region, Perfect Blue does this sometimes, as do other teams, you can brute force 4 more bytes if you're like on the same system as the program you're exploiting. Also used to brute force the address of Libc, or anything that either Pi or ASLR can both be dealt with via LSB overwrites. The one thing to be careful of is if null bytes are appended at the end of your input. So example 3.c, you can see that this reads until you get a new line, but it does not write the new line because it's while C does not equal the new line. So if the new line were appended, or if a null byte were appended to your input, it would be much more difficult to do correctly, and a brute force could still work, but you would only be able to write 2 total bytes and then brute force the new line until the input is randomized to end at your new line, or the address has the new line in it, place you want. So we're gonna demonstrate this in an exploit. Solve.py. So we need to send, yes, it is being recorded. So what was I wanted to look at the code. We need to send some number of bytes. So and then we need to send our new line. So we'll actually attach GDB. I actually have the number of bytes right next to me so that I don't need to look it up for you to make this a little faster. It's 24. Actually, I'm just going to demonstrate with 32 and see what happens. And I'm going to break at read input plus 47, or not 47, 65, I think. I'll double check this, but I'll show you exactly where that's coming from. Where's binary come from? Process. Where is, oh, I need to set my context. We love live demos, don't we? Been working fairly smoothly though, so I'm happy. Here we go. So we can finish the read and it errors because it overflew something, So this isn't breaking at the right spot, so we'll just finish read. And actually, we're just gonna break at read input and figure out the address we want to break at. Continue. I'm just gonna grab my solve because otherwise I'm gonna be debugging this too much. Alright, so yeah. This is, why is this? Backtrace. I'm just gonna break it, rename. Break the address, rename. Alright. Oh, what the problem is PwnTools is sending the input immediately, and it's obnoxious. P dot. Alright, I don't know why this wasn't doing what I expected to in GDB, but so we want to break at, so we're going to step through next instruction, and you can see that it is looping here, and it takes what we read, this byte at RBP, see RBP points to this address, minus 0x8, so that'll actually be this byte right here. It just read a 4-1, and it's moving that into EAX, so next instruction, it steps through it, and it's getting addresses to move it into. So you can see here, it just wrote the byte to this location right here. So we can, that's actually where we want to break. Read input plus 0x55 or something like that. Or actually, we want to break that last address. Read input plus 0x55 is 0x48. Not 0x48, 48. So we can continue as we're looking for our input. Nice long input so that we can keep doing this. So we can, if we hit continue each time, you see that this 4-1s keep growing up right here. Keep hitting more 4-1s. And the other thing you notice that changes is this counter right here. So this is our I in the for loop. And what's going to happen right here? The next one overwrites the I counter. And we start writing somewhere totally different. And our input is messed up. So what we need to do is figure out what value to set I to, because we are overflowing that and we need to overwrite a single byte in the return address. So we can continue, do the same thing. And the return address we want to write to is this guy right here. This A7 needs to become AA. So that is, we can actually just calculate the offset. So it's this address minus this address. And it's actually -1 because when we look at the code, we see the I is incremented after we write, not before we write. So we want to put 0x27 into this after 1, 2, 3. So 3 times 8 is 24 A's. If we look at solve.py, we can send 24 A's plus 27 is, we only need to write a single byte here because it only reads one character at a time. And then we want to send whatever the last byte of win1 was, which, if I remember correctly, was AA. So we can step through this in GDB again, continue. You can see it's growing each time here. And we'll overwrite the 17 in I to 27 right here, 27. And then this A7, hopefully, will be overwritten with AA. Yep, you see that it is. Then we can continue execution. And you see that it prints you win here. So that's this challenge. There were a couple hoops we had to jump through, which we see in a variety of challenges. Does anyone have any questions about that? ASLR, this is with ASLR enabled. All of the challenges I'm working with have ASLR enabled because that's a system-wide thing. But it also has Pi enabled, which is the main difficulty in this challenge because that is the address of our code itself. But because Pi is enabled, we can find the address. This is an example that I built myself for this demo. But we can find the address of, so we print win, and we print, we don't actually need to care about this. We only need this last single byte of win, which is what we write to. And the return pointer, we can figure out like exactly where we're writing there. We can continue here. So info frame shows us what our saved RIP is. And then we just find that up here. So we can see that this is the same address as this. It's also just right after RBP. Or it is RBP, yeah, right after RBP. But, so I just matched this up with this. And so figured out the offset here. And wrote AA in here. Step through this again because it's kind of satisfying to watch. ASLR is generally the same. You can generally treat it as the same on every system. There's a couple weird quirks on different systems, like whether or not libraries are next to each other or not in randomized space. ASLR only randomizes this part of the address. So the address is different every time, but the last 4 bits will be, last 12 bits will not be randomized. So ASLR is actually just a scam. I thought I tried to. I don't know whether you picked that up. I was like answering 2 questions at once. But that was, I found the just print win will have this, and then I used the info frame to find what the saved RIP was, and then I just cross-referenced that with this where it is actually in the stack. I didn't need to brute force anything actually, because these bits don't change every time you run it. So you can see that this program will work every single time. Continue, it prints you win every time, because every time we run it, although the whole address of win changes, so you can see, so when is that this time and this last time? See, these addresses are different, but the least significant byte and this last half byte do not change. So we just overwrote the return pointers least significant byte. And this challenge, it worked well because everything else stayed the same. Sometimes you're returning to a faraway location in the binary, so this approach won't work without a little bit of brute force. And sometimes a null byte is appended after your input, in which case this approach would also not work, so it would clobber this 7. Does that make sense? So just the summary of that. Last 12 bits are from the elf itself. We can overwrite the least significant byte easily and brute force a couple more if we wanted to, which this example didn't go over. And gotta watch out for anything appended to your input. And the final example we're going to go over today is leaking Libc and the global offset table. So if we look at our code first, do you think you could find what the bug is? Meanwhile, I'm going to be pulling up my notes. Oh yeah, the reason ASLR doesn't change the last bytes is because of the page size. Yep. Thank you, Rowan, for answering that. Where was I? Example 4. Perfect. All right. So, did anyone see the bug here? I'll give you a hint. It's the exact same as the very first example. There's the index that we are reading from and writing to is not checked. But in this case, we are in the BSS section. You can see this is an uninitialized variable, an uninitialized array up here, which means it will be loaded in the BSS section, which is always initialized to 0, and it is not very close to our code. So we don't have, and there's no relationship between it and the stack. And so what we can do here is related to a ret to libc attack. I'm going to explain this first and then explain got just as a refresher, and then we'll go through and actually try to exploit this binary. So for a ret to libc attack, what that looks like is you overwrite the return address to an address in libc, which we didn't talk about very much today. It was mentioned some during Rowan's reverse engineering, but libc is a library that has a bunch of useful functions like system, which we saw called a couple times printf, and like that. And we can call some of those functions if we know their addresses. And so it's basically the exact same thing as win2, but instead of calling win2, we call the function system from libc. ASLR does randomize the address of libc. That's basically ASLR's big main feature, which is quite helpful for protection. We can also use partial overwrites to help in some cases there. Libc is shared, yes, but it doesn't on Linux. It will be the address will be different for each program still. When like a fork occurs, there's some randomization in some cases. There's some ways to call a fork where it won't end up getting randomized, but in general, starting a new process will change the randomization of it. But on Windows, like dynamic libraries, if you leak the address of one, you know it in all programs. Also useful in libc's, binsh is in it. So if you have the address of like the function system, you also have the address of binsh, which can be convenient. And as a side note, you can just use the string sh sometimes too. And a libc leak basically always required in a CTF. If there's a pwn challenge, if it's a non-trivial one, there's a high chance you're going to be needing to leak a libc. And if there's a CTF with pwn challenges, there's a near 100% chance that at least one of them requires leaking libc. And for a ret to libc attack, there is usually you need to ROP to set up arguments if you're on 64-bit, like we demonstrated with Win2 in example 2. But in 32-bit, you don't need to deal with any ROP because arguments are passed on the stack. So that tends to be a somewhat easy solution if it's possible in 32-bit challenges. And so now I'm gonna give you a summary of GOT. So this slide was also in Rowan's RE presentation. Great slide. Went through a while debugging it and making it look beautiful. But the way GOT works is there's a PLT and GOT. PLT has short code snippet that basically says jump to this address that you look up in the GOT. And so it tries to look up an address in the GOT. If the GOT will default to the address of a fix-up, and that fix-up will set the value in the GOT to the actual address of printf, and then it'll call the PLT entry and call printf. This is because with ASLR, you don't actually know the address of any libc functions. So it'll look it up each time you need them. And you can see here that it will, once it loads it once, it'll just be able to look up the same address every time. But the thing is, the GOT needs to be writable for this to happen. And if the GOT's writable, then we can write to it, and we can change the address of printf, say, and make it system. So when the function tries to call system, it calls printf, or vice versa, because we want system to happen. So if we look in our example, if we manage to make, say, input or free system, and then we set our input here to binsh because it just reads into our input, then we could call system binsh, because free is a library function which is looked up in the GOT each time it's executed. So we're gonna, we're gonna look at this in the actual example. The example 4. We look at this is what the code looks like, but GDB, we can run. Which number do we want to write to? So print printf and PLT. So this is the value at PLT, but put the ampersand, this is the address of printf at PLT. And printf at got.plt. Hopefully this works. Bummer. We can use PwnTools then. Actually, is it calling printf? Yeah, it is. Okay. Example 4. So e.symbols. And we could see it should have its got.printf right here. And we could print this as hex. So this is the offset. This is actually, I believe it is compiled with pi. This is the tool checksec, which when you load it in GDB, it actually tells you what protections. I was going to mention this earlier, but quite useful. Command checksec will sometimes work if PwnTools installed. Sometimes you can just use it directly from PwnTools or GEF. But this is so this is a writable address, and it is relative to run 1. All right, so we're back in main. So this is numbers. This is our array of a bunch of numbers. Nice. Here are all of our numbers. We wrote a 1-to-1. But we can look at minus 64. We need parentheses. What is it? Oh, we do want add numbers. All right. This needs to be cast to avoid. All right. So we can see these are actually, this will be, it's too bad we don't have symbols here, but we can see like this is the address of malloc. This is the GOT right here. Some of these addresses. And you see like this is the address of printf. This is the address of malloc. This is the address of setvbuff. These are all the library calls we're functioning. All the library functions we're calling. Library functions we're calling. Okay. Yep. So these addresses are also writable. And if we look at the index from our input to this, it actually wasn't that far off. So I subtracted 128, but let's just print a lot more. All right, so this is where the address of numbers, and this is the address of something in Libc. And so it's OX50 divided by 8 because we're using longs in the example. So OXA is 10, so this is -10. So if we run, we're writing to -10, and we'll write like a 1 to it. We'll print something and we segfault because we're trying to execute memory at 1 because our IP is 1 because we're calling printf probably. And it's looking for 1. So now what we need to do is write a solve script as per usual. Example4.py from pwn import star. A lot of times we'll have templates, solve scripts, so like you just set like variables, binary, and port, remote, stuff like that. And like set up command line arguments, like pass the debug command line argument to debug it easily, and so that you don't need to just comment out and keep recommenting gdb.debug, for example. But in our case, I just want to make a nice example for you guys. We're going to be needing to use Libc and calculate Libc offsets in this one. So I'll demonstrate how we find the Libc that's being used on your system. So it's linked with some certain Libc. If we use the LDD command, list dynamic dependencies, something like that, you could see this is the Libc that it was linked with. So we can load that into PwnTools, call it Libc, and we'll be able to treat it exactly like a binary. So we can look at libc.symbols. There's a ton of things. And they're all addressed by a base of 0. So like the first thing in libc is address 0, last thing's whatever address. So we'll need to perform some math and get a leak in order to figure out what the actual libc address, what the like real address is. So we can, first it asks us to write something. So I'm actually gonna copy paste this because so this will just read and write. Tends to be helpful to write functions like this to easily interact with a program. If you need to like do like if it has a loop, need to do multiple things, stuff like that. But this just writes and reads. So first it asks us to write. So we're gonna write 1, 1, just to get past it, because what we need to do first is leak something. We will get the offset, so we can do, because I printed the addresses in GDB of what, like where numbers was and where like some got entry was. But not libc, PwnTools can do this for us. So binary.symbols, a got.a2 ASCII to long. So this is the address, the offset of ASCII to long in the binary. So a2l got equals, and then numbers equals binary.symbols, numbers. So the offset between them is numbers it was a2 got minus numbers divided by 8. This is the index that we need to write to. We'll call this index, not offset. Because a2l got is greater than or is less than numbers, this result will be negative. So we're going to be writing to like negative something. Example 4.pi, we're writing to -8. And we actually probably want this as an integer, not as a floating point number. There we go. And we're going to make this a string as well, because we need to send it to our, okay. So now we can just a2 leak equals read index. So you can see the read, all it does is just reads until gets a caret and then sends this. It casts it to a string for us, but should be good. Then we're going to print the index here. Index. Leak equals a2l leak. And we're actually going to print this as hex. This reads it, but we need to see. Yeah, we need to cast this to a integer. And I don't know what. String object. Why is it a string? It's not a string. It's an integer. It's being an integer here. Oh, this is a dot, not a comma. It needs to be a comma. That is funny. So I think a dot just tries to concatenate. Or no, it's calling the function. So it's trying to call a to l dot hex like it's a class. But that's not what we want. Is there a reason I use Jeff instead of PETA? I found Jeff works better. I've had issues with PETA in the past. But I hear the best two are Jeff and PwnDebug. I actually hear PwnDebug is supposed to be better than Jeff. And from reading their docs, it looks like it is, and I'm gonna at least tinker around with it. But Jeff works and is very quick to install as well. Haven't used PETA for a while, so don't remember how painless it was. Where was I? So yeah, we have the leak of ASCII long. We can actually check, but I'm not gonna bother in GDB right now. We are going kind of late. So now that we have a leak of Libc, we need to start calculating what our offsets are. So we want to convert A to L, or we want to convert free, or A to L should probably be fine too. We want to change the address in GOT to the address of system. So we need to find the address of system. So what we'll do is we'll get the leak minus libc dot symbols. So this just subtracts the libc dot symbol. So this is, if it's at the very beginning of libc, this will be 0. If it's somewhere in the middle, it'll be whatever offset it is in the libc. So this will get the base address of the libc. So now we can just take system plus libc dot, this is libc base plus. Libc dot symbol system. And this should, all right, at this point, I'll show this in GDB. I need to set context again, don't I? All right, so we're just going to continue here. All right. And we'll print the address of system and print the address of A2L. So we can actually compare. This is what we leaked here. And this is what we have here. That's the same. And this is our calculated address of system for E0, port E0. So we have the same address there as well. And now we just need to write our system address to something. So we can write, we're writing what where, so we're writing system adder to, let's just make it A to L, because example, yeah, because we have input, and then it'll call, no matter where we input or input, it'll call ASCII to long on it. So this means that we have system and we control the argument. We control the argument because it's read here in fget. So you can see here, if we run it, example 4.py, we have GDB attached still. We're just gonna, it's erroring because I messed up my code. Offset, it should be index. Continue. All right, so it's continuing to execute. And now it's just asking us for which number we want to write to. So we can send /bin/sh, because actually we should be able to. Let's see, GDB might not, yeah, symbols aren't there for the GOT. But if we believe that this will work, we can run /bin/sh, and we need to continue. And it does execute system, and as you can see, we have who by default, we are running, having gotten a shell. And so that example shows how to leak libc using the GOT, which is one of the most common ways to read if you have an arbitrary write or can read something from like an offset in BSS, because it is very close in memory to it. So it shows how to leak the GOT with libc, and then use that leak to write to the GOT in order to make it think that a different function is libc. So actually, I'm going to break it. Continue, break. We're going to break it A to L at PLT. Continue, the words /bin/s. And you can see here, we're trying to read from this address, which is this address, which is in the GOT table. So we can look at this address. We can print it as an instruction. You see that it's system. It's not A to I like it's supposed to be, because we successfully overrode it. And we can step through, next instruction, and you see we're at the stop of system. We can continue, and we are in a shell. So those are my 4 examples. Here's just a summary of those libc offsets so you can see it as a simple summary. PwnTools useful. You just elf libc, you get your leak somehow, and then you can calculate the base of the libc by subtracting the address of the symbol that you leaked. If you don't have a symbol, but you know like the offset in libc, you can use GDB to calculate that by hand, and you might just have a raw number here rather than libc.symbols. And then you can calculate any address in libc with libc base plus libc.symbols system, or whatever address you wanted to, whatever symbol you wanted to calculate. If you don't have the symbol again, you can just pick a number by hand. Sometimes you might want to like ROP with libc, and it's the exact same idea. You just add the offset of your ROP instruction. I'm not going to talk about format strings, so that will likely happen on Friday. So any questions? If not, then thank you all for showing up, and play CTF on Thursday.
Dark
Dark
CTF.
CTF. That's the one.
Sweet. All right. Thanks, everybody. We will see you on Friday for the next one. Oh, I guess if there's questions, yeah. What is the next point from now on? After you get good at this, how to take it to the next level?
Practice. Win CTFs. It always gets harder. Like, you can make more and more complicated challenges, and so after these categories, we're going to talk about perhaps heap. I don't know if I'm going to be able to get too in depth on heap, but like format strings, heap exploitations are complicated. Railrow, uh, we will talk about, I don't know if it'll be directly in bypassing railrow, but that example can deal with partial railrow, but it can't deal with full railrow. But I'll mention that tomorrow, or not tomorrow, Friday. Not sure whether or not I'll be able to have a specific example dedicated to it though. Injecting code in the binary without user notice, that is shell coding, usually. And yes, and without user noticing, you can set up shellcode to do it, or you can set up a ROP to call a shellcode, or you can configure your ROP to not crash after it returns. So yes, there are a ton of different ways to do it, but our goal is to just get a flag in a CTF, so I'm not gonna care about what happens to my program after I get a shell.
Yeah, if you want to do code injecting without the user noticing, uh, that's a little bit outside the scope of CTF. That's more of a
Yeah, you can do it like append code to the binary. Uh, Basically you get a shell, and then from the shell you modify the binary directly. That's a lazy way of doing it.
yeah, one of the easiest ways. I don't know about without user notice. That takes a little bit more work. And typically, if you want the user to absolutely not be able to notice, you're going to need to be hijacking a set UID binary, which is already harder. Um, but the best way to do it typically is to memory map some data. If you have set UID, you can memory map some data, inject your code into that, and then fork and exec your code from memory so that you can start a somewhat hidden process. But that also requires you to have a rootkit and access to the kernel and things like that. So it's not a simple task. It's a big undertaking.
You won't be able to just change a binary without someone noticing because, for example, they could take the hash of it if they know, if they're like actually paying attention.
Yeah.
But like you can change the binary and like change addresses in a way that it still does what it's intended to do. But yeah, Dark CTF starts Thursday. Hopefully it's good. If there's
Cool.
no other questions, see you guys later.
All right. Stream.